So I'm Adrian Tate. I'm the lead of the Cray EMEA Research Lab. This is Stig Telfer from StackHPC. So we're going to give a joint talk today. Originally, we were also going to be joined by Lena Oden from Jülich, and she's no longer able to make it. So we will sort of try to weave some of her material into our talk. And I just want to recognize that this is work by a lot of people, so the HBP team, and various people from the Cray EMEA Research Lab as well. So the original plan would be that Jülich would give you an overview of the HBP and the PCP process and a description of use cases. And then I would describe some of the co-design work that we've been doing on explicit data movement and the storage system. And then Stig here will describe one of the subcontracts of the project, which was to work on configuration and evaluation of the Ceph storage system. And we'll have significant time for Q&A. Actually, it's grown to be probably more than significant time for Q&A because the next session has been canceled. So we are planning to take our time here. So if it gets really boring, just throw stuff at us and we'll speed up a little. Okay, just a little disclaimer first. So everything I describe, at least on the Cray side, has got absolutely nothing to do with Cray products. So please don't go to your local Cray salesperson and ask for a Ceph storage product because it doesn't exist. And salespeople being salespeople, they probably will sell one to you anyway. So let's avoid that. And the other thing is that, so although this project's been going on for quite a while, it wasn't until we were able to enlist StackHPC to work on the Ceph part of it that we actually had a decent performance Ceph file system and storage system. And so actually, many of the results you're about to see are very new, super hot off the press. And some of the things that we hope to show you today are even not available. So we will try to pull those results into the slides that we upload online. But despite that, we were very happy to come here and share this with you because we think evaluating Ceph as a possible HPC storage system is basically of interest to the community, and we want to share the results, even the negative ones, with you, and hopefully give rise to a decent discussion on that topic. So, if you don't know what the PCP is, so the Human Brain Project, when they first described the technical requirements of their systems and their software stack, they used an EU funding vehicle called the PCP, the Pre-Commercial Procurement, which is designed to help public institutions procure services and goods from private companies when there's a significant R&D component remaining in the development of them. And the idea would be that you use the EU funds to then move ahead and productize some actual development. There was a phased competition. In the final phase, which resulted in hardware, Cray won one of the awards, and IBM and NVIDIA won the other. And very broadly, the technical objectives of this PCP were to study dense memory integration and interactive supercomputing. It's also worth pointing out that this is now several years old. The technical requirements of the Human Brain Project have moved on significantly, and there's a follow-on project called Phoenix, which is going to really work on the next generation requirements, and hopefully the work that we describe here you'll see in a follow-on as part of that Phoenix project. So as part of our Phase 3 award, Cray delivered a system into Jülich called Julia, which is a Cray CS400 system. It has 60 KNL nodes. It has 4 visualization nodes, which are Xeons with NVIDIA K40. It has 4 data nodes, each of which has got each of which has 2 Fulton Dale SSDs, which has each of which has a capacity of 1.4 terabytes. Your number is different, isn't it? Okay, I think you're right. So it's 1.6 terabytes per device. It runs the Intel Omnipath interconnect version 1. And it has a highly diverse software stack that was installed by Cray as a special one-off sort of R&D effort, including a large amount of machine learning software and data analytics packages and things like that. And it has a very interesting, diverse memory and storage system consisting of obviously the typical Xeon memory hierarchy of caches and DDR, but then the original plan was that we would study Apache Pass non-volatile memory from Intel, which didn't happen because that hardware was delayed. And we have two different types of HBM. We have MCDRAM on the KNLs. We have GDDR, high bandwidth memory on GPUs. We have on-node flash on the KNLs. And we have, as I said, the Fultondale SSDs on the data nodes, which together provide primary storage for the whole system. And that primary storage is basically provided by Ceph. Why did we look at Ceph? Well, primarily it's to study a novel experimental storage system, and in particular an object store. But there's an additional requirement because we wanted this to immediately be in production as a file system. And so Ceph sort of wins in that it has CephFS, which is close to production POSIX compliant file system. And you may have heard that CephFS does not particularly perform well. And I think that that was a valid complaint maybe a year or two ago. But what we found is that by running standard benchmarks, CephFS actually appears to be performing reasonably well. It's a very nuanced conversation, but we're interested in, is it in the same ballpark as a Lustre file system running on KNL? And the answer is yes. Ceph has excellent support from different vendors and across the community, especially in the cloud community, and has this very interesting set of interactions with cloud software, especially OpenStack. So, the use cases for the Human Brain Project, actually, there are many of them, but the use cases in particular that are relevant to this sort of Ceph and storage system are these three. So the first is interactive visualization of brain simulation data. And so there's a package from the Human Brain Project and the Blue Brain called Brian, which is an I/O interface to two visualization frameworks, RT Neuron, and something called Brains. One which does rasterization and one which does ray tracing. And this Brian package has a set of different key value store backends. Currently, they have memcached and level DB. And the goal of this project was to introduce Ceph as a resilient key value store. And that work has now been done mainly by Jülich. I'll say a little more in a second. The second project is deep learning and I/O caching supporting it. And this is part of the probabilistic Atlas Ubrain project at Jülich, so you can follow this to find out more. The high-level idea is that the brain is sliced into very thin slices about a micrometer thick, so you get about 7,000 of them per brain. And then they use microscopic techniques to stain brain regions, and then look at the whole picture of how the brain is divided into these regions. They do this across multiple brains, and then they use a convolutional neural net to basically learn how to do that classification itself. And the classification problem works well, so neural nets can learn to do that to a relatively high accuracy. The problem is that each slice contains a significant amount of data. And the total training data size that they need to use is something in the region of 50 to 100 terabytes. And this dominates the entire workflow. So the investigation here was to use Ceph object store as a cache, because there is actually data reuse both within the model and across models. And so they would just use Ceph Rados to load chunks of data that they know can be reused later. And then on the next iteration or the next run of the model, just simply load it back in. And again, this works effectively, has an effect on both on training time and I think on model accuracy. The third use case is another visualization following neuro-simulation, but this one using the Nest neuro-simulation package. So the middle and the bottom pictures here describe how it is currently done today, and the bottom where they intend to go, where they want to go. And the idea is simply that Nest simulates a network and produces output. The output is membrane potentials and voltages. And that data is stored into primary storage. And then later, a neuroscientist will load that data from primary storage and perform some kind of analysis, usually a mapping of brain activity onto brain region, and possibly a set of related analysis, such as just creating charts and then discussing with their colleagues how the model needs to be varied so that experiment and theory would more closely align. And then they need to feed back into the model new sets of parameters and keep repeating. And this is today a manual process. So the model basically has to be stopped, restarted with different parameters. Where they want to go to is that Nest is basically producing data into a live streaming pipeline. That data is automatically stored for later. And the visualization is a constantly running program that receives the most up-to-date information as it's available. The user, the neuroscientist, will perform the analysis in exactly the same way, but then can basically also publish updates or recommendations to the simulation back into the pipeline, and these are automatically incorporated into the running Nest application, which then adapts. Obviously, this is very experimental. So the summary of these three use cases is that the first, the Ceph key value store backend is roughly 3 to 4 times slower than the in-memory key value store, which is probably not a surprise. And it's debatable as whether that's a positive or negative result, right? It's apples to oranges comparison. Use case 2, we don't have data, but the caching of data through Ceph Rados affects the load time on the second iteration to the point that they described it as successful. And we know that if Ceph was to move towards supporting a local cache tier, then this would become quite powerful. And use case 3 requires significant R&D. And I will say a little more about that. So there was a phase 3B to the PCP project. Basically, as I said, there were significant hardware delays, and that also delayed a significant amount of R&D, which was great because the technical requirements of the project moved on, and so we basically signed a new contract to do a more up-to-date sort of co-design effort around things that were now topical. That consisted of looking at explicit data movement technologies to support that use case 3, and with the intention of making this a productizable development that Cray could use as a product in the future. Part 2, to configure and evaluate Ceph, which we subcontracted to StackHPC. I said that CephFS performs well. I also said it's a fairly nuanced situation, but what we're looking for with this is that, especially general benchmarks such as IOR perform within the same ballpark as Lustre on the same hardware. And here you see the top two lines, POSIX random and sequential reads, obtaining roughly 4.5 gigabytes a second, which I can tell you is in line with what we see on KNL single node IOR results on a Cray XC with KNL. So you can see a more detailed version of this if you like, but we're relatively happy with CephFS. So how many servers we have? How many final servers? Interesting. So in terms of explicit data movement, I think it can be a confusing area for people. So why would we want to start looking at explicit data movement when we have good storage systems and we have MPI communications within jobs? And the point is that HPC, for the past 30, 40 years, has really been preoccupied with a very particular type of optimization, which I sort of caricature here. So the top line is basically a serial job, which consists of I/O, parallel execution time, and the red being serial execution time. And the role of HPC is basically to flip those parallelizable pieces across resources to compact what we call time to solution, with the limiting factor generally these days being the number of memory channels that you can parallelize over. And vast amounts of research into algorithms, into programming environments, into compiler design has enormously compacted this bottom metric, which is time to solution, the running time of your single algorithm. But time to solution doesn't correlate very well with scientific throughput. Scientists have always known this, and the reason is quite simple. So if we look at the example of numerical weather prediction, then they have a variety of different jobs that perform very different computational functions. And a very simplified version of that would be that they have data assimilation, which then produces data passing into a set of ensemble forecasts. And the ensemble forecasts produce output that is then used in a product generation. And time to solution describes the performance of one of those ensemble jobs. So it's very important, but it does not describe how the scientist is able to obtain results. And that metric instead we call time to insight, which has largely been ignored by HPC. The HBP equivalent of the same workflow would be neuro-simulation, producing data to a visualization, which then requires some feedback into another neural simulation. So basically, just like use case 3. So Cray customers have increasingly been asking us to start looking at this broader problem. And of course, this is a very general and very hard problem to look at. But the key piece to go in here with is the severe lag time between passing data between workflow components. And this is basically a fairly manual process, and where they rely on the parallel file system for communication purposes, which, as you know, is not very good use of the parallel file system. And so Cray customers have been increasingly tell us to get involved at that point and to do what we do best, which is to provide high-performance communications over the fabric for moving data between workflow jobs. They don't care about fancy workflow managers that will require, GUIs and expensive classes in 6 months to learn. They just want low-level enabling technologies to help them compact that overall schedule. And so in collaboration with some of our customers, we came up with an experimental data model called the Cray Data Object Model. And the goal of this is to introduce some level of very lightweight data model that customers could use to immediately perform explicit data movement. And later, when we build tools on top of it, to actually do some rather complex orchestration of data around a memory hierarchy. And the requirements were that they wanted various levels of abstraction to interact with. It has to support a large variety of data formats. And it actually has to support data in very different forms, such as data in memory, so basically arrays, or files that we interface only through POSIX, and data that's already in a data model like HDF5. And so that already then becomes a very complex problem. So the user of this would annotate their code, and they do this in a way simply to describe the data that is already there. There's no new data structure introduced that they would ever have to copy into, and this is obviously a requirement for HPC. So through the entire data object model, we would require no copy. The hierarchy is fairly simple at the moment, so the CDO, core data object, is the top-level abstraction that the user interacts with. An intersectional data object is what we will use to understand how data should move around a network, and a TDO, a transport data object, is what we will actually move. The user only really cares about the top one. So we have an umbrella project in this area at Cray called Octopus, which I will not go into in a lot of detail, but basically this is going to build on the Cray data object model to try to perform some of that orchestration of data. And the idea would be that today, two jobs running on a Cray system have this type of relationship where all we know is that there's a data dependence between job 1 and job 2. And so in order to go a little deeper, we have to annotate the codes with the Cray data model, which then, at the bare minimum, would give us a sort of an object view of input and output data for the two jobs. And we'd already understand that the data dependence is between specific data objects. When we know that, we can do one of two things. So we can allow explicit data movement on the part of the user, or build in a higher level tool set, which is where Octopus is mostly interested. We can understand where in the memory hierarchy it would make most sense to place that output so that job 2 has it at the earliest opportunity. And we can even get involved to make sure that the jobs are launched appropriately with the data already in the correct memory. That's the goal of Octopus. And basically, we see this as adding some traditional HPC magic into the workflow space. Now, as we began working on the Octopus project with customers, we realized that there are underlying technologies that are missing that would significantly advance our own tool set and also would be very interesting to the community. And so we developed something called the Universal Data Junction, which is open source on GitLab, and anybody that wants to contribute to that can. So just come speak to me and I'll help you find it. The idea would be you have a core data object and you want to move it to another core data object. So at the top level view, they're completely abstract. But as you dive in, the first CDO will be distributed across M nodes. And will, according to some distribution scheme like contiguous or block cyclic distribution. And it will be in a certain format, like it will be an array or HDF5 or conduit or file. And then on the other side, of course, that data object might be distributed on N nodes, also with its distribution, and also has its own data format. So the general problem of moving that data across all of those different combinations is non-trivial, to say the least. And that's the problem that UDJ solves. And basically, the idea is to short circuit to mostly prevent the parallel file system being needed at all, and to perform direct data transport. So we have 5 different transport methods. 2 of them are not real transport, they're actually virtual shared memory. So data spaces is one, and this was the first one that we implemented. We've also done something with H5FD DSM, which was developed here at CSCS, and does not work properly, which is why it has an asterisk. MPI is our main focus, of course, because this really truly allows zero copy and high performance transport over the fabric. And we have a Ceph RADOS transport, which could be very useful if we actually decided that we do not want to go over the fabric, because the fabric is also a valuable shared resource that we need to protect sometimes. And then we have file-based transport, for baseline purposes. Now, those of you that are interested in this field will have noticed that there's another complication here, which is how you take data from M nodes in its own distribution and convert it to N nodes in another distribution, which is a non-trivial problem. And you can already see that here. So if you take a producer set of data, which has been block cyclically distributed with a block size of B1 times B2 across M1 by M2 nodes, then you can see any particular process, in this case, element 1,1 of the producer grid, owns a rather weird non-contiguous set of data. And that same data needs to be converted into or transported to a consumer grid. So if you take an arbitrary element of a consumer grid, in this case 0, 0, again, it's a very strange non-contiguous set of data. And if you were to look at the whole set of data that needs to be transported, on the left is one CDO, distributed in one manner, and on the right is another distributed in a completely different format. In the middle is basically the intersection of the two. And for any different process pair, that intersection is really what we care about. So the pink is basically the overlap, the intersection of both, and the pink data is what actually needs to be moved between that process pair. So the Cray data object encapsulates all of the information needed. The CDOs are the entire data set and their distribution. The IDO is the pink data that actually needs to be moved, and the TDO is each individual piece of the IDO that gets transported over the transport interface and may be aggregated according to what the transport interface sees on the network. So a couple of results for you. So this is UDJ with the data spaces transport, doing a variety of M to N node data redistribution. You'll see that in this case, M and N are equal, just for convenience, so it's actually M to M node, but with different block sizes. And what you see is a rather confusing sort of set of spaghetti. But if you just aggregate it, you'll see that things sort of max out at between 1 and 2 gigabytes a second, which is way under the network bandwidth and way under the injection bandwidth. So it's not really surprising. So data spaces is producing or generating a virtual shared memory server. The data is being moved there, then the data is moved out to the consumers. So it's actually a very important use case, because when we want to start using non-volatile memories as a staging area, this is probably one way we will do it. But in terms of fast transport from one set of nodes to another, it's not the best option. MPI-based transport, on the other hand, looks very good at the moment. So I've overlaid our data with the OSU bandwidth numbers, the red line. And that really is a close approximation to injection bandwidth. And what you can see, so if you look at the one producer to one consumer line, the purple, we converge with the injection bandwidth. So we hit the hardware limit for large sizes. For small sizes, the difference between the two lines is pure UDJ overhead. And we have histograms to fully understand what that overhead is. And we have a good plan to reduce it. So hopefully you'll see the purple line approach the red. And then for increasing numbers of nodes on producer and consumer, you see a linear increase in bandwidth. This is a log2 scale. So UDJ RADOS transport, can you see the lines? So unfortunately, the system we do this on has been down for a while. So it was my real goal to show you RADOS transport here today. And I'm not able to do so. So I can promise to you that I'll upload the RADOS transport chart to the online slides. And my prediction is that it looks very much like RADOS bench performance, which you will see in Stig's upcoming slides. Use case 3 has been implemented with UDJ. So we have this now sort of live streaming of UDJ puts and gets that allow Nest to push data. UDJ will asynchronously store them for later on. And when the analysis is available, the neuroscientist will be able to take this live data and use it for visualization and other purposes. The feedback loop into the Nest application is not currently there. That would be the next step. So my summary. So first of all, the PCP system, Julia, is installed, functioning, and Ceph is now fairly performant and fully functioning. Ceph performance varies, I think, between great, respectable, and poor. We will try to clarify that over the coming months. The HBP PCP requirements show that explicit data movement is absolutely required. Requirements from other Cray customers show this too. And this Cray data object model that we are experimenting with seems to show some promise as being a way to enable traditional HPC tools and expertise to be used in a wider setting. And my prediction is that time to insight will become the second metric of HPC success. So I just want to acknowledge the great work done by the Cray team on UDJ and Octopus, and the great work done by Stig on Ceph, and acknowledge the three projects that fund this work, which are obviously the HBP PCP for the conduit interface to UDJ, Plan for Res, an EU project, which has allowed us to work on the data model, and Expertise, an MCSA IATN project, which has allowed us to work on the data M2N node redistribution. So that's my talk. Thank you very much. I'll pass over to Stig.
I can use this one.
Ah,
is it working?
Good.
Thanks, Adrian. So let's take a little bit of a closer look at the Ceph cluster at the core of this machine, and look again from a different perspective about why Ceph is kind of interesting here. And one of the main things that is interesting is that Ceph is the poster child of software-defined infrastructure, software-defined storage, and so on. And it underpins a whole substrate of really useful, adaptive future technologies, which can come into a HPC environment from the cloud environment and bring about innovation and bring about flexibility and enable the users of these machines to access their data in very different ways, which is kind of what Adrian was outlining as well. So more generally, so Julia is obviously, the use case is very much about something which is internal to the system and is a conduit between the compute nodes, the Knights Landing nodes, and the visualization system as a sort of a hot cache. But generally, there was a really good slide from yesterday, from Monday, from Colin McMurtry, which was describing the CSCS system architecture. And that slide had OpenStack, an OpenStack cluster, at the heart of the network. And really, that kind of ties into this idea that a modern HPC data center kind of has two cars in the garage, which is you have a conventional, tuned, optimized HPC environment, and you have an OpenStack system which kind of serves with as maximum flexibility every other requirement of the data center today. And the two kind of balance together, but the best practice, the ones that work really well, are the ones where the data can flow freely from one to the other. So either we bring out the HPC-enabled storage, or we bring in the Ceph cluster into the HPC environment. So this project, this experiment was interesting, certainly to me, and I think generally in a range of ways. So this is how I visualize the system. We've got the 60 Knights Landing nodes on the right. We have a number of the other nodes. There's a visualization cluster, the Omnipath fabric in the middle, a couple of login nodes. But the interesting pieces for me are these data nodes, and those nodes are where we're running the Ceph object storage daemons, and so these ones are really delivering all of the data and taking all the data from our storage cache. I think Adrian was absolutely right to say about how these things have come on. This is a slide from an excellent Intel white paper which came out last month. And what it tracks is the progress of Ceph as in terms of performance and the progress of hardware along with it in the last 4 years. So we've gone from IOPS per server of 588 in 2014 on the Firefly release, all the way to 100,000 IOPS with a fairly recent Luminous release and all the most expensive Intel kit that they could possibly put into the configuration. That's 4 years of progress from 588 IOPS to 100,000. And Ceph's evolution is responsible for a very significant part of that. And it doesn't take much to look at this graph and see that there is a huge momentum in the way that Ceph is evolving. And that looks very promising for the way that Ceph's future direction is going. The other conclusion to draw from this graph is if you're not running the latest release of Ceph, you are definitely a step behind. The data nodes that we have are from 2016. They're Broadwell machines, 2-socket, fairly standard. We have the Fultondale P3600 NVMe devices, which are also a couple of generations behind where NVMe technology is today. The interesting piece is the Omnipath network, and we've been using the Omnipath network for both the front side of the Ceph environment and also for the storage replication environment as well. And principally, we've been using it using the IP over InfiniBand interface, so we have a TCP transport messenger. So the data nodes also host a number of the other supporting services, the monitors, the managers, the metadata servers, and so on. But it is the object storage daemons that are the interesting piece here. And the way that we've divided the machine up is to split each of the NVMe devices into 4 object storage daemons for Ceph. This enables us to get a different kind of balance, to strike a different balance in terms of the network to the CPU to the storage devices. And that's a very tunable thing, and it's definitely architecture specific. We came up with 4 to the device, and I think that was based on information a little bit like this, again from an Intel white paper, which shows the dark blue is a configuration similar to ours. The gray is 2 OSDs per device, and the light blue is only 1 OSD dedicated to an NVMe device. So this graph shows that in most cases we made a good choice, but we do burn a bit more CPU, but it doesn't seem like CPU is the dominant factor in the balance of this system. Yes, yeah, that depends. So we explore a bit on that coming on, so I'll come around to that. So the first thing we looked at was how does the raw system perform? Because it's always nice when we're looking at a machine to take these constituent components and look at how they stack up once all and compare it with the overhead of protocol, and then we know what kind of cut Ceph is taking through Rados and other things. We measured about 5,200 megabytes a second using FIO by accessing these devices locally across all partitions. And we get fairly good evenness across all the partitions as well. But then we looked at the network performance, and this is one of the seriously limiting factors on this machine, was the use of IP over IP. Definitely, you don't see 100 gigabits on the Omnipath network interface. The best we get is about 50. The other interesting piece here is that half the time we would get 50, and half the time we would get something around 25. We've had a pretty good scrutinization of this. We can't really see what the limitation is there. It's certainly not NUMA residency, and it's certainly not IRQ placement, because I've changed all of those in both directions, and it doesn't seem to affect anything. The other interesting piece to look at here is when you look at the Knight's Landing in the top right corner, when they're communicating with each other by IP over IB, we get about 6 gigabits a second on the 100 gig link. That is iPerf bandwidth. So this is after TCP protocol. That's something that we need to bear in mind through all these results, that the network transport that we're using is very asymmetric in terms of what it's delivering to between the nodes. So when we compare the raw storage of one node, that's the read aggregate read capacity, and the IP over InfiniBand performance, we can see that they're actually kind of comparable, but there is this huge error bar on the variation of the IP over InfiniBand. And I think that's causing us a little bit of variability in some of the results that we're getting. So we started looking at this Ceph optimization project last summer. And back then we were running Dual and the Filestore backend for Ceph. And we had started to have a look at what we could do to take that system and try and do what we could to elevate the performance on it. So first thing was, obviously, we need to get onto the latest release, and we need to use some of the new technologies that have come in through it. In particular, this name of Bluestore. If you're in the Ceph world, you will know of Bluestore, and if you haven't, you've been under a rock or something. But this is a new way of for Ceph to store the object data locally on the drive. For reproducibility and ease of configuration, I used the Ceph Ansible playbooks, although they don't support the kind of storage arrangement we have with 4 SSDs per device. So what I was doing was I was adapting those, hacking into place the architecture that we want. So I'm using an adapted form of the Ceph Ansible playbooks here. So the first results that came through from this machine, when we upgraded to Bluestore, to Luminous rather, didn't really look very encouraging. And this is kind of where we were middle of the autumn last year. So we see that with Luminous we get a much improved performance in terms of the latency and the bandwidth on small object transactions. And we see that for both writes and reads. So there has been the previous graph on the evolution of Ceph's performance kind of confirms that the Ceph architecture is performing very well when we move to newer generations. But what we don't see is any uplift in the overall system bandwidth, and that was kind of turgid. And we're not going to linger here very long because we have better things to look at. The obvious thing to do next was to move the system onto the new storage backend. So we replaced the OSDs one by one with the Bluestore backend, which is this block-oriented storage model. So Bluestore is kind of designed to optimize a hard disk and SSD-supported architecture. But we have an all-flash configuration here, and people have reported not seeing a huge advantage in terms of what Bluestore can do, but we still seem to find some benefit. And while we were there, we also managed to do a system upgrade and went to newer Omnipath firmware as well. So one of the interesting things that Bluestore claims is to reduce the level of what they call write amplification. So what we're looking at here at the top is protocol bytes in Rados, test going over time. So this is seconds along the x-axis, and we're seeing about 1,000 megabytes a second, but it's very, very irregular. But what we see down here is if we actually jump into the storage servers themselves and we capture the IOs queued to each of the block devices, then we can see the aggregation of what's going on in order to implement this, these Rados writes. And we can see that there's about a 4.5 times factor of amplification in terms of bytes of protocol versus bytes actually written to the disks. So that's the big limiting factor in using Ceph. The reason for those 4.5 is, broadly speaking, 2 for writing to a journal and then writing to the Filestore itself, and then 2 because this is a 2-way replicated pool, and then 0.5 because of the XFS overhead of the Filestore. Yeah. Like those spikes there. Exactly. Yes. And journaling was going to 3 OSD servers. So those spikes, those downward spikes, are very interesting. And what I can see is that it is not the storage devices that are the problem. So when we look at the I/O stat and we look at the completion of IOPS down there, what we don't see is an increase in queued but unserviced IOPS on the devices. So these spikes, or these cuts, are coming from Ceph itself somewhere. But I'm not sure exactly where, but perhaps someone does know. Yep. So when we looked at Bluestore, if we superpose the performance we got versus the previous graph, things are looking a little bit better now. And this is a one-way replicated pool, but so it does actually automatically have an advantage. But what we're seeing is performance which is now approximating, it's in the same ballpark as the raw performance of the devices themselves. So now we have a 2.5-way replication, or a 2.5-way amplification factor here, but we're getting just over 4 gigabytes a second at peak in terms of writes, and reads are roughly similar. And the interesting thing to observe, I've just drawn on the side of the graph there, is what we see is that we are now within the range that we are saturating the capabilities of the IP over IB link as well. So perhaps that is a limit, and what we'll see is that limit is on the receivers for IP over IB, not the transmitters. The machine that we're using, or the way that Euler is being used as a hot data tier, really. So what we can use this for, instead of replicating this data, we can actually just use one-way replication. And given that this cluster is entirely internal to the project, we can do away with the CephX authentication as well. And that gives us a nice uplift. So what we see here, these are single client results, by the way. What we see here in the orange line is a pool with no authentication overhead and one-way replication, so no resiliency introduced to it either, just persistence to one volume. That gives us closer to 5 gigabytes a second in terms of write performance for one client, and about 4 gigabytes a second for one client on reads. But this is what is interesting about this graph is that it doesn't tell all the story. So there is another curiosity, which kind of ties into what you were saying then, Hussein, about the performance over time. So if we look at the way that the objects are getting written over time, we see that we're starting at approximately somewhere between 4 and 5 gigabytes a second. And as time progresses, suddenly we go down into this cliff, and we see these large injections of delay. These are RADOS object commit latencies. So we're getting sort of 70, 80 milliseconds of delay for a commit, whereas previously it was about 5. These are kind of interesting, and I think these tie into another graph from the Intel white paper I was referring to, where we're comparing the P3700 in the top right corner with the new Optane. So we've got the 3600, so I assume that it's one step behind where the 3700 is there. But we look at write bandwidth over time, we can see these sharp downward spikes and these sharp increases in latency, in commit time there. So that's quite interesting, and you can easily ascribe that to a attribute of NVMe technology of that generation. And what you can see with the newer, the sort of 4800, the Optane devices, is that they are, for no great significant increase in bandwidth, they are far more consistent and far faster in the latency and the commit times. So that's something to look out for. When we looked at, so single node performance is kind of interesting to a degree, but this machine is serving a cluster, and we want to really look at one of Ceph's strengths, which is how does it scale out. And so we looked at, so here is the results for one visualization node versus two. And we can see that for the write performance, what we're getting is no significant increase there. But for the read performance, we get a very good scaling, and we were getting almost double the performance on the reads there. The story is pretty similar when we look at the Knight's Landing nodes. So what we can see here is that the writes seem to peak at about 4 gigabytes a second, which has been fairly flat from where they were at the start. So we aren't actually getting much improvement in the overall write saturation performance. What we are seeing, though, is that the reads are scaling very well indeed. And those data points at the end there, I mean, getting on for 16 gigabytes a second, the machine's raw devices are capable of delivering about 20. So we are very close to saturating the SSDs there, which is pretty good. I wasn't expecting to get anywhere near that. So there's obviously some interesting work to explore on where the write performance is going here. And there's obviously some interesting work to explore around this kind of curious hysteresis at the top of the graph, where we're flipping between a fast mode and a slow mode for long periods of time. One part of that, I think, is going to be in relation to the IP over IP networking. So that is definitely the next stage to look at. The other is, I think it's kind of interesting. I think what this confirms is that there is the bottleneck for IP over IP is certainly on the reader side, not the transmitter side. And we can see that when we're fanning into the storage cluster, we see a no elevation in performance, whereas where we're fanning out from the storage cluster to the compute nodes, we do see good scaling there. The next piece was to look at actually unlocking the capabilities of a performant fabric and ditching IP over InfiniBand and going for the RDMA transport, which has been in Ceph for a couple of years, there or thereabouts, is based on verbs, but it's I think for a long time now it's been in a just about working state. It hasn't really made it into production, but now since Luminous, you can actually get access to the IB verbs messenger protocol using the standard CentOS RPMs, which is a huge boost. So now we don't have to build our own. There are bug fix trees around which you can use to improve it, but what you get in CentOS and Luminous now is good for running IB verbs. So I had a good go with this. The configuration you need is pretty minimal, actually. I mean, 3 lines in your ceph.conf, a few lines in the systemd services, and enabling page pinning in the in user processes to a greater degree, and then you're good to go. I had a go on this on 3 different RDMA-enabled machines. Luckily, they each have a different different network architecture. So the Julia system has 100 gig Omnipath. I had to go on a 100 gig InfiniBand system and a system with 25 gig Rocky as well. The 25 gig Rocky was the only one that actually worked out of the box with the unmodified RPMs, and it worked pretty well. I mean, I didn't have any usability problems with that. The other two, I think, come down to some portability issues with the way that the verb's Q-pair initialization is being handled. So certainly the InfiniBand implementation, we get to a point where everything initializes, the Q-pairs are created, but nothing can be transmitted over them. The Omnipath implementation, the parameters that are passed to the Q-pairs are static. They're not using a connection management abstraction, and so they get rejected by the kernel driver when it's loaded. But I think, I mean, connecting it or implementing the connection manager in these in this driver is not going to be difficult. It's not a hard system to work with. So I don't see any reason why this system couldn't be generalized to run more comfortably on all three by adapting it to the connection manager, and that's what I've been looking at recently. So going on to the 25 gig Rocky system, I have some results from using the RDMA transport instead of TCP. This machine is a very different architecture. So firstly, we've got 25 gig Ethernet and Rocky for a start, obviously. But also the OSDs that we have in this machine are only running off 3 far lower spec SATA SSDs. So this machine is actually wholly I/O bound, whereas the human brain system, the Julia system, is wholly network bound. So it's actually the wrong machine to be looking at this of all. And that kind of reflects in the data. So the green line is the RDMA messenger protocol, and what we can see for writes is that actually there is no difference, simply because we're only getting to the SSDs a little bit faster. For the reads, we can see the top of the graph is line rate at 25 gig E, and we can see that all, both using TCP and using TCP with jumbo frames and using RDMA Rocky, they all pretty much race up towards line rate very quickly. The Rocky one, you can't really see it on this graph, but it's about 10% quicker, up to about 64K or 128K. But then actually it drops off, and it doesn't achieve anything quite so close to line rate as using optimized Ethernet with the Mellanox 25 gig NIC. So that was kind of disappointing, but at the same time, these are the wrong metrics. So what we need to be looking at here is, are we offloading? And when we're offloading, are we saving CPU? And the model there, the thing that we're shooting for is, can we use a Ceph cluster and deploy it in these nice automated cloud-native ways on our compute nodes in a hyper-converged kind of manner, and then use it with RDMA in a way which gains us minimal extra overhead for processing the OSD load. So running with the CPU, so the next investigation stage for me here is to look at what is the CPU consequence of using these with some representative benchmarks. But this is not the human brain machine, so I didn't have access to the applications there. So finally, what I was going to say is the big slide to bear in mind here is not the one that I did. It's the Intel progress of Ceph over time. It's going to get there. There's huge momentum behind what Ceph is doing. Already today, we can get 75% of the raw device capacity through the RADOS protocol. That's pretty good, and that's comparable with HPC file systems. The RDMA, in most cases, but not in the human brain systems case, is probably not going to give a great advantage if the system is limited by disk I/O. What it should do, though, and I haven't proved this yet, but what I expect it to do, is to deliver lower CPU overhead so that we can use Ceph in new and interesting ways. The Ceph file system, finally, is improving dramatically. So the Luminous release is the first one where it's approaching sort of production level of stability and production level of POSIX compliance. So I think that's one to watch. And the idea that you can create these things in auto-provisioned, flexible, dynamic ways as part of a software-defined deployment of HPC clusters is a pretty cool concept to shoot for. So I think this is one to look at. Okay, I think that's all we had. Thank you. Do we have any questions? Rados bench. So the principal aim of this project was the object bandwidth, the low-level object bandwidth. And so Rados bench is the tool to use for that. In terms of the higher-level constructs, you know, the block devices, the file systems, actually you can use things like IOR, and they will give you a very good sort of connection, a native connection to RBD, and also connections onto a POSIX file system. So what I tend to use is those packages as stimulus, so Rados bench or IOR in its various forms, and then focus on the instrumentation. So using things like perf, using things like IOStat and so on to understand what's going on behind Ceph on the raw devices.
I'm no expert, but our studies of Rados bench made us think it really could be improved significantly, or that another object store benchmark could be developed, because we were not able to glean a great deal of information from it. Okay.
This is all replicated. So I think erasure code will come into its own with a slightly larger cluster and certainly a more capacity-oriented cluster. What is interesting here, though, could be to use erasure coding in order to change the balance between CPU, network, and I/O, given that we can spend a bit more CPU and have a bit less I/O. But I think one of the interesting things with erasure coding is also something I was going to say, actually, which was around here. These kinds of tailing off when we get to larger object sizes. So erasure coding will chunk stuff up and stripe it. And so I think you should actually see that kind of falling off for very large objects, or reasonably large objects, actually being changed significantly as a behavior with erasure coding, but I haven't investigated it to this level. The other thing to say about this is that if you're using something like the Swift API or the S3 API, you're coming through Rados Gateway, and Rados Gateway is going to be striping your S3 or your Swift object into pieces anyway. So Rados Gateway should be configured to chunk it up around about the sweet spot around here, or slightly shorter than that, and then you will actually get you would all avoid this kind of dropping off bandwidth where Ceph is not dealing well with large object sizes and not processing them effectively. So, so these are, that kind of dropping off behavior is an artifact of using the low-level APIs rather than using the ones that people would conventionally use, which would be Swift or S3. Hi. This is all done with TC-malloc, I believe. So we didn't change those. So the main areas of focus that I had were to do with the placement, the numer awareness, because if we look at the system, what we have is the Omnipath NIC is over here, and what was happening was that the IOQs for the OPA NIC were all coming to one core on the Broadwell, and so the first thing we did was to kind of spread them out across that one socket. And then we were experimenting with where should we put the OSD processes, and actually what we found was you can kind of sweat this stuff, but actually letting the IOQ balance and the other things find an equilibrium worked pretty well as well. So that I don't think that actually that time was well spent for the efficiency as it recovered. Any others?
Thank you very much.
much.
Okay, thank you.